We can describe vector fields as contravariant vector fields or as covariant vector fields. We know that we can go from one to the other. It is customary to describe them as covariant vector fields, which we have called also differential forms, and are also called one forms, with the index down, transforming covariantly. Then the transformation law of this field is completely fixed by the definition that we gave, and it takes this form. So a prime mu of x prime is a nu of x, okay, of x prime, so everything is written in terms of x prime, and times the inverse Jacobian matrix. Okay, and this is completely valid for any kind of coordinate transformation. So in particular for Poincaré transformations, we have that they are given by this expression. So this is lambda mu nu x nu plus a mu. But in this transformation rule, we need to express x as a function of x prime, also to compute the inverse Jacobian matrix. So we have to invert this transformation, and first we take a to the left hand side, and second we multiply the whole expression by the inverse Lorentz transformation, lambda minus 1, okay, with the index mu and an index alpha. Okay, these are numbers we can put them on the right or on the left. This is clearly, if I write lambda minus 1 alpha mu, lambda mu nu, this gives me delta alpha nu, and delta alpha nu times x nu gives me x alpha. So here I'm going to get x alpha, and in the right hand side, sorry, in the left hand side, I get lambda minus 1 alpha mu x prime mu minus a mu. So this is the form of the inverse Poincaré transformation in general. Then we can compute the inverse Jacobian matrix. Since lambda is constant, a is constant, the second term that you get, lambda minus 1 a, is constant, the derivative gives you 0, and this is just lambda minus 1 mu. Okay, here it is x alpha, so I would have to change alpha by nu in order to get this. Now we go to the general transformation rule that we have above, and we find that this is lambda of x prime, then we have a nu, and we can write here lambda minus 1 x prime minus a, and this times lambda minus 1 mu. So this is how the vector field transforms under finite Poincaré transformations. Now we can see what happens with infinitesimal Lorentz transformations. So if lambda mu nu is delta, well, it's equal to delta mu nu plus sigma mu nu. Okay, let's write this as matrix like this. So sigma is very, very small. Then we can see that lambda minus 1 is 1 minus sigma. If you multiply one by the other, you get 1 minus sigma squared. But to the first order in sigma, this is just 1. So we want to write this in components. This is lambda minus 1 mu nu is equal to delta mu nu minus sigma mu nu. So let's go here and substitute, and we have a prime mu of x prime is equal to a nu of x. Okay, this this is x, and delta nu mu minus sigma nu mu, which is a nu of x. Now nu is replaced by mu, and we multiply by delta, minus a nu sigma nu mu. Then this means that the the infinitesimal total transformation, which is a prime x prime minus a of x, is just minus a nu sigma nu mu. Okay. Then using the standard universal formula, which tells us that this is delta tilde mu minus delta x nu partial nu a mu, we find that this is minus a nu sigma nu mu minus delta x nu. Delta x nu is x prime nu minus x nu, and remember that this is delta nu rho plus sigma nu rho x rho minus x nu. So this term is going to cancel this, and this is nothing but x nu rho. Oops. I forgot. Okay, this is the infinitesimal lambda nu rho, but there is still an infinitesimal translation, so there is an x nu minus alpha. So this is alpha nu minus x nu, which is still cancelled with this, and the infinitesimal transformation has this form: sigma nu rho x rho plus alpha nu. So this is sigma nu rho x rho plus alpha nu, and this multiplied by partial nu a mu. So we can write the result here. Delta a mu is minus a nu sigma nu mu minus sigma nu rho x rho partial nu a mu, and then the term that takes into account the space-time translations. So this would be delta of a mu. Now, in dealing with the vector field, we have for the first time to face a problem of which we talked about in one of the previous videos, which is the mismatch between the components of the field, which is imposed by the fact that we are dealing with unitary representations of the Lorentz group. This gives us, in this case, 4 components and the number of degrees of freedom that we want to represent. So if this is a massless vector field, we know that it represents particles of spin 1 that basically come in 2 types, with helicity +1 and -1. So these are just 2 degrees of freedom. And then we have 4 functions to describe it, just 2 degrees of freedom in 4 dimensions. Another problem that one can see is that the extra functions that you have here are associated, if you want, to particles with the wrong sign. Another problem is that these extra functions that you have are associated to particles that have negative energies, etc. They give you a lot of problems. So you want to eliminate these extra functions, or you don't want, or you want that to make them irrelevant Then we have to remember that the effect of having gauge symmetry. Okay, remember this box is that you have less independent equations of motion. Okay, and this was the effect of the second Noether theorem. And this is associated to less degrees of freedom. So the solution to this problem, which happens for the first time as we consider fields more complicated than the scalar field, in the vector field, the solution is to include some gauge symmetry. Now, instead of inventing gauge symmetry just from somewhere, we remember that the vector field, okay, that we know so very well, is the Maxwell field. The Maxwell field describes photons, and it does it very well. And we are going to see that it has some gauge symmetry. We know that if we describe the electromagnetic field through the field strength, which is defined in this way, so using this notation of symmetrizers and antisymmetrizers that we presented in one of the videos, this is just okay, let me write it more clear. This is just this expression. Okay, you can check that it transforms as a tensor 2 times covariant, which is also antisymmetric. So there are Lorentz transformations, which are the ones which are more relevant. Here F transforms in this way. And if we compute this total infinitesimal transformation, we find that this is minus F mu rho sigma rho nu minus F rho nu sigma rho mu. Okay. Now, in order to use this notation that we have introduced, we can write this as minus 2 F mu rho sigma rho mu. Now, I am doing this just for your benefit, just to show you how this notation works. Here we antisymmetrized 2 indices which were consecutive, but here we want to antisymmetrize mu and nu. Well, I have to show you that this term is really this one with the indices interchange, but this is not so difficult, okay, because this is equal to minus F nu rho sigma rho mu, okay, because this is antisymmetric. And now you compare this term and this term, which come with different signs. This comes with a minus, this comes with a plus. One is the other after the interchange mu nu. Of course, if F mu nu is antisymmetric, this transformation rho has to be antisymmetric. And so we are going to express it in this way. There is a factor, there is a sign minus sign at the beginning. There is a factor 2 because there's a symmetrization or antisymmetrization comes with a factor 1/2, and here there is no 1/2, so there must be a factor of 2, and the rho is not affected by this antisymmetrization. So these bars here mean that nothing in between is antisymmetrized. Okay, and the antisymmetrization only affects these 2 indices. If I had written F mu rho sigma rho nu, this would be completely different because I would be antisymmetrizing in these 3 indices, an operation that I still haven't presented, but that can be done, of course. It exists, but it gives you something different from what we wanted. Okay. So a covariant tensor of rank 2 in this case, which is completely antisymmetric in its indices, is called R form. So in this case, F mu nu is a 2 form. So this is different from a 1 form, or what we call a differential form, because a differential form only has one index. So they are also called 1 forms because 2 forms exist. And this is one example. Now, something important, a very important property of F mu nu is that it satisfies a constraint because of its own definition. Let me write it for you. This constraint is has this form. With now I'm going to permute all the indices cyclically. So now I move everything to the left. So it is nu f rho mu plus partial rho f mu nu, and this is equal to 0. We are about to prove this, and you can prove it just by brute force. Okay, let's do this first. So this would be partial mu, and now we remember that this is partial nu a rho minus partial rho a nu. So this is rho minus partial mu partial rho a nu. Now the next term is the same, and now we start making cyclic permutations of these terms. So this is partial nu partial partial rho a mu minus partial rho partial nu partial mu a rho plus partial rho partial mu a nu minus partial rho partial nu a mu. And let's see what this gives. Now partial derivatives commute, so this term and this term just cancel because they are the same, partial mu partial nu partial nu partial mu. Then I have here mu rho and rho mu with opposite signs, so they also cancel, and here nu rho and minus rho mu. Okay, so they also cancel, and indeed this is 0. So this is probably the moment to introduce the notation that I mentioned before. We can write for these 3 indices, okay, a complete antisymmetrizer, and this is defined as 1 over 3 factorial. All the possible permutations of these 3 indices are 3 factorial because there are 3 indices, and you have 3 factorial terms, the first of which will be partial nu f nu rho, and then terms that you obtain by permuting these indices and affected, because this is antisymmetrization, this is our square brackets, affected by the sign of the permutation. So we have partial mu f rho nu. Just not to make mistakes, let me write this below, f rho mu, and then I interchange these two, f mu rho, and then plus f rho mu nu minus partial rho f mu mu. So this is the definition for any tensor f nu rho. However, in this case, this term and this term are the same because this is antisymmetric, so I get a minus sign, and a minus is a plus, so I get this is 2 times partial mu f nu rho. By the same token, this is 2 times partial nu f rho mu, and this is 2 times partial rho f mu nu. So I get a factor of 2 that cancels one of the factors of 2 in the factorial, and this becomes 1 over 3, and this plus partial rho f mu nu, these cyclic permutations. Now if I multiply this by 3, I get that this is what I have written here is just 3 times partial mu f mu rho. And if I do it in this way, I write this identity in this way, it is much easier to prove that this identity is satisfied, because I have that partial mu f mu rho is 6 times partial mu a rho. I have used that f nu rho is 2 times, so here I have it, is 2 times this antisymmetrization, and of course this is antisymmetric. I put it inside a full symmetrizer. I don't need to keep this symmetrizer anymore, everything is antisymmetric. And because this is the same as partial mu a rho, because these derivatives commute, and at the same time, if I interchange these two indices, because this is antisymmetrized, I should get a minus sign. I find that this must be 0. Okay, so this is very easy to see. So this is an identity which is always satisfied for any fields. I haven't used any equations of motion, and these kind of identities are called Yank identities. Okay, something we should already know is that these Yank identities give 2 of the Maxwell equations. So they are indeed equivalent to 2 of them. When you the Maxwell equations are typically given in terms of an electric field E and an electric field B. When you rewrite them in terms of a potential, 2 of them are automatically satisfied. They are solved in a sense if you use an electromagnetic potential. On the other hand, we know that from the physical point of view, the electromagnetic potential, this vector field, is more fundamental than F mu nu, the field strength. We will also see what is the relation between the field strength and electric and the magnetic fields. Okay. From now, if we choose to describe the electromagnetic field with the field strength F mu nu, which contains E and B, we will see how. Then we see that if we change A by some A mu prime, which is obtained from A mu by adding the partial derivative with respect to mu of some arbitrary function, so any function chi, then if you compute f prime mu nu, which is 2 times partial mu of A prime nu, and now this is 2 times partial mu A nu plus 2 times partial mu chi antisymmetrized. Now this is F mu nu, this first term just gives F mu nu, but the second term is 0 because of the same effect that we noticed here. You antisymmetrize 2 partial derivatives. Since they also commute, then this gives you 0. So this leaves invariant the field strength, and because this transformation depends on an arbitrary function, not a constant, okay, or some fixed functions. This is a gauge symmetry. This is the gauge symmetry of the electromagnetic field. This is a gauge symmetry that will allow us to remove two, or makes redundant two of the degrees of freedom, but then we can safely work with the full A mu, as long as we preserve this gauge symmetry. Two of the components are really not there. They are only there for the sake of preserving Poincaré symmetry. Now, so this is where this gauge symmetry appears. This is a very important symmetry. Okay. Oops. And the next thing that we have to do in order to connect this relativistic perspective of the electromagnetic field, which is described by this tensor F mu nu, and the classical representation in terms of the electric and magnetic fields, we have we are going to describe the relation between F mu nu and E and B. So a tensor and antisymmetric tensor F mu nu has two kinds of components, okay, related to the time. I mean, from the point of view of the time component. So there are components which include one time component, 0, and there are components with no time component, so Fij. Okay. There are 3 of these, and there are also 3 of these. How do I know this? Because there are only 3 possible combinations of 3 numbers taken antisymmetrically. So you have 1 2, 1 3, and 2 3, because 2 1 is minus 1 2, and so on. So there are 3 of them. The idea is that these 3 components can be associated to a vector, a space or spatial vector in R3, or if you want in Euclidean space, 3-dimensional Euclidean space, better than R3, and the same here. Okay, how do I do this explicitly? Well, I define, and so these definitions are a bit convention dependent. I define this 3-dimensional vector field as Fi0 with the indices up. Okay, remember that each time we raise a spatial index we get a minus sign. Each time we raise a time index we don't get any signs, and this is antisymmetric, so this would be minus Fi0, and this would be plus F0i. So just for you to know. And the other vector field, it's Bi, and it is defined, okay, with this factor 1/2, the antisymmetric symbol epsilon I j k and fjk. The 1/2 is used, so for instance, if I have B1, then this is epsilon 1 jk, but jk is summed over 2 3 and 3 2. They appear 2 times, so this one just cancels this thing. The minus is again conventional. Okay, the inverse transformation, so the inverse relation, if you want, this is okay. This is the definition to remember. The relation between Fi0 and Ei is obvious. The inverse relation between Fij and Bk is Fij is equal to epsilon I j k Bk, and with a minus sign. Okay, how do I know this? And this is another mathematical interview, or that You need to know this in order to make explicit computations. So let me check that this is correct. So I compute minus epsilon ijk, and then I have bk. Bk is minus a half epsilon. Now in this formula I have to replace I by k, so I have k, and let me call the other two indices I and j. This doesn't matter because I and j are contracted, so I can call them whatever I want. So if you prefer me to call them Lm, I call them Lm. In fact, I should, because I am living here, I am using I and j, so I better do it. Okay, so Lm and Lm. This gives me 1/2 because these two signs cancel, and then let me write kij k. Because of the total antisymmetry, if I put this k at the very beginning, this means interchanging j with k and I with k. These are two minus signs, so I get a plus. I can also see it as a cyclic permutation. Cyclic permutations of three indices, three antisymmetric indices, do not give you any sign. So this is the same as epsilon k ij and epsilon k Lm FLM. Now there is a formula that tells you when you contract what happens when you contract these two antisymmetric symbols with one index or two indices. So let me write this formula. So kij epsilon klm gives you 2 times delta ij comma lm. What is this? So more notation. So this is 2 times, and this is 1/2 delta il delta jm. So first with first, second with second, minus delta im. So first with last, delta jm. Okay, so it looks a bit strange. I'm not cancelling the factor of 2 because I want to rewrite this with 1/2 in another way. Observe that this is the same as if I interchange ij here. Sorry, this should be jl. So if I interchange I and j here, I get the second term. So I could also write this as 2 times delta put it like this, I L delta J M. So this is antisymmetric in I and J. But also if I interchange L and M, I also get the second term. So this is 2 delta I L delta J M. Both things are 2. This tells you that anyway this thing is both antisymmetric in ij and also in lm. So this is what this symbol is, and you can view it as the unit matrix in a space which the labels, instead of just being one index, are pairs of antisymmetric indices. So when the pair ij is equal to the pair lm, you get a 1. When and if ij is equal to ml, so the intersection, you get a -1. And if they are different, you get 0. So it is almost like the Kronecker delta, but instead of for simple indices, for pairs of antisymmetric indices. There are generalizations of this that we will see and that we will have to see. For completeness, what happens if I contract two indices? So I have KL, I, epsilon, KL, J. Okay, it is easy to see that if I contract this, so this means that K is equal to K, L is equal to L. So this is only different when I is different from L and K. So it is the other index, but if this is the other index, it must be equal to j, because these are the same as this. Okay, this means that, well, you can check this, that this is just delta ij. And if you contract all of them, you get 3 factorial. Now, of course, you can, from this formula, you can find this by setting two indices equal, and from this formula you get this, because when you make I equal to j, you are summing over this index. They take 3 values. This gives you a factor of 3 times 2. This is 3 factorial. Okay, so this ends the mathematical interlude. Let's put this here. And going back to this identity, this means that this will be 1/2 okay, of 2 times delta ij lm flm, and as I said, this acts as the identity as the Kronecker delta in the space of antisymmetric indices. So this means that the antisymmetric pair lm will be replaced by ij, and this cancels, so this is just fij, which is what we wanted to prove here. If you are not convinced by this calculation, use this definition and you will see that you get exactly the same. And my advice is that you don't trust me and try to do it yourself. Okay, check that I am right, or prove me wrong, and please tell me if I am wrong so I can fix this video. Okay, this will be the electric field, and this will be magnetic field. With this convention for the electric and magnetic fields, the tensor f mu nu can be written in terms of them as follows. So remember that this would be f00, which is 0, and here we have f0i, this is the 0th row. Here we have fi0, so it is minus f0i. Okay, these are the first 2 row and the first column. Then we have another 0, and here we have the f12 and f13, and here minus f12 minus f13, another 0, and here f23 minus f23 and another 0. So this is what this matrix looks like, and then this means that we have 0, and f0i is ei, so here we have ei, here minus ei, zero. Now f12, according to this formula here, is minus epsilon 1 2, and then it has to be 3, so it is b3, so it's minus b3. Then f13 is minus 1 3 2. This is a permutation from 1 to 3, so it is plus, so it is plus b2. And here we have b3 minus b2, 0, and finally we have f23 is minus epsilon 2 3, and then 1. This is 1, so a minus. This is minus b1, b1, and 0. Okay, I don't think anybody will use this very often, but we had to do it. What is more interesting is to study the transformation laws of the Lorentz transformations of the electric and magnetic fields. Since they are part of this electromagnetic tensor, they will transform under Lorentz transformations. So if we just study, we are going to study only Lorentz boosts, and okay, we would proceed as follows for the electric field. We want to find what the components E prime are, EI prime, then this is by definition F prime I 0. We are using upper indices, so they transform contravariantly, and we have by definition F mu nu. Now we have to decompose these indices mu and nu into zeros and i's, j's, k's, etc. So let me start first with the index mu only. We have lambda I 0, and I still keep this lambda 0 nu, F 0 nu, plus lambda I j, lambda 0 nu, F j nu. Next, I decompose this index nu both here and here. I get lambda 0 I, and then well, if nu takes the value 0, then this is multiplied by f. It will be multiplied by f 0 0. So this nu has to be a different space index. So lambda 0 j f 0 j, and here since f already has one space index j, this can be time or space. So we write lambda I j, and then we have lambda 0 0 f j 0 plus lambda 0 k f j k. Okay, once we have decomposed all these terms, now we identify these components again with electric and magnetic fields, because this is what we wanted, to find the Lorentz transformations for the electric and magnetic field. This F0j is minus EJ, so we have minus lambda I0, lambda 0j, EJ, plus lambda ij, lambda 0 0, and this is ej, plus lambda 0 k, and then we use this inverse relation here. If I raise the indices ij, both indices, then I don't get any signs, because I get a sign for each spatial index. So this is a minus epsilon j k, and then I need a third index, L, for instance, L B L. Okay, this is the first part of the calculation. The second part is to use the components of the Lorentz boosts, and we know that these components are, because we have found them before, this lambda 0 0 is 1 over the square root of 1 minus v squared divided by c squared, which we are going to call gamma, which is the traditional name, but just because it is shorter, and we don't have to write so many things. Then lambda 0 I is given by minus v vi divided by c times gamma. And lambda I0 is minus vi divided by c. Finally, how about lambda ij? This is delta ij plus vi vj divided by b squared gamma minus 1. So this is a simple way of writing the components of the Lorentz transformation. And then we just plug these expressions into the transformation of E prime I. So we have E prime I equal to minus, and minus times minus is plus, so this is Vi over C. Sorry, this is I forgot a gamma here. VIC gamma, and lambda 0j, which is again a minus, Vj over C gamma, and then Ej. So this is the first term. The second term gives me I am going to write lambda ij in a slightly different way. So I write delta ij minus vi vj divided by b squared. Okay, and then plus vi vj divided by b squared gamma. So now this term multiplies lambda 0 0, ej lambda 0 0 is just gamma, so it's gamma ej minus lambda 0k is minus and minus, it is a plus vk divided by c gamma, and then epsilon jkl bl. Okay, since we have this kind of contractions between velocities and vector fields, we introduce the notation E parallel. I think we have done this before, as vi divided by v. This is a unit vector in the direction of the velocity times ei. So it projects the electric field in the direction parallel to the velocity, and E orthogonal is the complement. So it is delta ij minus vi vj divided by v squared times ej. So we can always reconstruct this, because ei would be vi divided by v e parallel plus okay, I forgot the index I here, so plus ei orthogonal. So this would be a way to reconstruct it. Now, using these definitions, we have that this formula here can be written in this way: E prime I equal minus gamma squared divided by c squared, and then you have vi v I need to multiply and divide by V. And then we have E parallel. Next, I have the product of this thing, which is the projector on orthogonal directions of epsilon j. So I have plus gamma epsilon, E I orthogonal. Then if you multiply this term, the same term here, okay, now we multiply it by this term. Okay, delta just replaces j by I, but this term vj, since it is multiplied by epsilon and there is already a vk contracted, gives 0, because you have two v's contracted, which is a symmetric product contracted with this, and gives you automatically 0. So you have plus vk u1 gamma epsilon I kl vk bl. Then this multiply, now we multiply this term by this, and we get gamma squared plus gamma squared and vi divided by v, and the parallel component of E, and the product of this term by the last term gives you again 0 for the same reason, because you have two v's contracted with an epsilon, and symmetric times antisymmetric gives you 0. Now these two terms will combine. First of all, I think I have forgotten a factor of c here, and these two terms combine into gamma squared 1 minus v squared divided by c squared vi parallel plus gamma ei orthogonal plus gamma plus epsilon ikl vk divided by c bl. Now this is as we have said several times, equal to the component I of the vector product between v and b. Now if it is the vector product, the only part of b that survives or that contributes is the part of b which is perpendicular to v. So let's write this instead as b divided by c vector product b orthogonal, and then the component I. Okay. So gamma, and this is almost the result, because now we want to decompose E prime I also into the parts parallel and perpendicular. Okay, oh sorry, gamma squared and this factor, they just cancel each other, because gamma squared is 1 over 1 minus v squared divided by c squared. Okay, so now if I decompose E prime I into the parts parallel and perpendicular, I have to multiply by vi. If I multiply this by vi, this term clearly survives. This has the same direction. So in fact I will get, oops, this should be divided by v. I get that E prime parallel is just this term. Okay, why? Because this is perpendicular to, by definition, perpendicular to the velocity, and also this vector product is perpendicular to the velocity because it is one of the factors. So the rest is automatically orthogonal to the velocity, and this is given by EI orthogonal plus the vector product of V divided by C, B perpendicular I. Yeah, let me put the square brackets. Okay, so this is an interesting result that we also want to frame, and we just have to repeat the same thing for the magnetic field. This calculation is going to be a bit more complicated because it involves the epsilon symbol from the beginning, but let's just go. We take the definition of the magnetic field, and now primed. So it corresponds to F prime, and we simply use the transformation rules of covariant two tensor. So it transforms with lambda minus 1 and index mu, j lambda minus 1 and index nu, k, and f mu nu. Then we expand these Lorentz transformations. We have to expand these indices mu and nu, and we do this step by step. Okay, so first I expand the index mu, and then I get 0j. This one stays as it is for the moment, we don't touch it, and we have f0 nu plus now a special index I is taken, so I use L and j lambda minus 1 nu k f L nu. Next we expand the new index. So this now stays as it is, and first I could take nu equals 0, but since I already have a 0 here, then I will get 0. So this has to be L, for instance. In this term has not been used, so it's f0L plus now I am done with this first term, so now we expand the nu in the second. First the nu can be 0, so we get lambda minus 1 Lj lambda minus 1 0 k f L0, and then I have another term plus I still have minus lambda minus 1 Lj, and now I need another spatial index, so for instance m k f L m. Okay, so this is the expansion, and now I start identifying fields. f0L here. Okay, if I look into the definitions that I made, f0L is directly EL with the index up, so minus half epsilon I j k, and then I have lambda minus 1 0 j lambda minus 1 L k and E L. Then if that was EL, this is minus EL, Lj lambda minus 1 0 k el, the minus sign, and this L should be up. Okay, now before I move to the next term, observe that the difference between this term and this term is that they have J and K interchange. So one is the anti-symmetrized, is the term that would obtain if one interchanges J and K and changes the sign. So this whole thing is antisymmetric. Since this is contracted with J and K, and anything contracted with J and K would be antisymmetric, this first term already is antisymmetric in J and K. So this term and this term are the same. And I can delete one of them and just add a factor of 2. Okay, we get rid of this term because it is already contained in this factor of 2, and move forward and consider this third term here. So this is plus lambda minus 1 Lj lambda minus 1 Mk, and FLM we can re-express in terms of B using this inverse transformation that we wrote here. So it is with a minus and epsilon. It is minus epsilon LM, and I need another index like this. So I change this sign, I remove this parenthesis, and I close the brackets. Now the next step will be, as before, replacing the values of these transformations. Let me separate these two terms. So the first term is just minus epsilon I j k, then lambda minus 1 0 j. Remember that the relation between lambda minus 1 is that I just reverse the value of the velocity. So I search in lambda 0 j, and it is here. So now I reverse the sign, so it is plus v j divided by c times gamma. Lambda minus 1 Lk is here, and it just takes the same form if I change it, because this is even under b going to minus v. So this is delta Lk plus VL Vk v squared, which multiplies gamma minus 1. Gamma minus 1. And all these multiplying EL. Okay, and the same for the next term. So it is plus 1/2 epsilon I j k, and we have two terms like this. So one is delta Lj plus VL Vj divided by V squared gamma minus 1, and the second term is delta Mk plus Vm Vk divided by V squared gamma minus 1 epsilon Lm Bn. Okay, this term, remember that we can combine this and this, and they give a projector in the projector in the orthogonal direction. So we have minus epsilon I j k. But anyway, before I do this, I realized that okay, this delta multiplied by this is okay. It gives me, I just have to replace k by L. Then this first term gives me Vj over C gamma and EL. But this multiplying this epsilon by Vj and then by Vk gives 0 because you have two V's repeated. So this is it. Okay. Then let me consider the next terms. This is a bit more complicated. I just multiply these terms by epsilon one by one, and that's it. So first the two deltas times epsilon gives me epsilon I, then I replace j by L, then I replace k by m. So this would be the first term, and then I have epsilon L m n b n. I am taking the convention that I don't distinguish between upper and lower. When I deal with three-dimensional indices, objects with three-dimensional indices, I don't distinguish between upper and lower indices. If it is a four-dimensional object with a spatial index, then I do distinguish between upper and lower, and there is a different sign. But here, it doesn't matter if it is up or down. Okay, the same for E and B. These are three-dimensional objects. I always write them with the index up, but it doesn't really matter. Then the next term, I multiply this delta and these b's, so I get plus a half epsilon I L k. Now k is not changed, and this is V m Vk divided by V squared gamma minus 1 epsilon Lm n Vn. Then there is another term which is similar, which is the product of epsilon times this term and this term, plus a half epsilon I j m V L Vj divided by V squared gamma minus 1 epsilon L m n Vn. And the last term contains the Vj, Vk contracted with epsilon I j k and gives 0, so that term does not contribute. Okay, now here we recognize the minus gamma and then the vector product of V over C and E and the component I. Then plus, and okay, in order to use the formula that I gave you before, I have to write this in the same order. I can move this index I to the third position, which gives me a plus sign. It doesn't change the sign, and this gives 2 delta I n. The factor of 2 goes with the 1. Okay, let me do it. This is delta I n b n. This goes, and this gives me bi. Okay, next. Okay, first let me see if this the last two terms are probably identical. So let me check this. First, let me relabel k here and call it j. So it is, I use the same indices that in the other case. So let me call now L I call M, M I call L. So I get I M J. This would be L, and here this is M L N. Now I see that they have the same indices but in different orders, so let me put them in the same order. I put this m in the first place, and this gives me a minus sign, and then I get mln, which is okay. And here in order to get the same order, I shift this to the first position. This gives me a minus sign, and moving m to the third position, this gives me nothing, a plus sign. So I get two minus signs, and then I get two terms which are identical, so there is a half and a half, so they add up, and then I get epsilon mij, then epsilon ml n vl vj divided by v squared gamma minus 1 vn. Okay, this gives me 2 times delta ij ln. When I write them with all the indices up, I write this a comma in between, so I distinguish between the first two and the last two. If two of them are written up and two down, which here does not make any difference, I don't write the comma, but it is just the same symbol. And I remind you that this is, okay, with a factor of 2, this is delta il, delta jn, minus, then I interchange either ij or ln, so delta in, delta jl. Okay, we'll do this in the next step. So I get minus v divided by c e I plus bi, and then if I take this first factor with deltas, I get plus, L becomes I, J becomes N, and then I have Bn, all this divided by B squared, and this gamma minus 1. Minus, in the second term, I and N are contracted. Okay, so B becomes Bn becomes Vi. I have the gamma minus 1, and then J and L become the same, so I get V squared divided by V squared, so nothing. Okay. Okay, I think I have forgotten these minus signs here, that I got this one and this one. This has a minus sign, so this has a minus, and this has a plus. Then this bi cancels this factor of minus 1, and we have minus gamma v divided by c factorial I. Then the factors that have a gamma is plus gamma, and then we have bi, or let me write it like this, b well, delta in, together with this one, minus vi vn divided by v squared vn, which I know is b, the orthogonal part of b, and then last term is plus vi divided by v vn divided by v vn. Okay, this is the last step. Plus gamma b orthogonal I plus vi divided by v parallel. Okay, so this was b prime I. Now we can decompose this into directions parallel and perpendicular to the speed, and we find that b prime parallel is only stays as it is. Okay, and if you okay, this is clearly perpendicular, and b prime perpendicular is gamma I minus V divided by C vector product with E. Okay, and again this deserves to be framed. And this is our final result for the transformation of the magnetic field under boosts. Now, just as a comment, notice that these transformation laws are the same that I would obtain if I interchange the electric and magnetic fields in this particular way. So E goes to B everywhere, and B goes to minus E. Okay, this is electric magnetic. It is the simplest example of electric magnetic duality. And it's a property also of the Maxwell equations in vacuum, as we will see. Finally, as I mentioned before, I said that this Yank identity that I wrote with the factor of 3 in this way was related to two Maxwell equations. To see if this is the case, now that we have relation between the components of F mu nu and the electric and magnetic field, we just do it. Okay. Also, that if I have these three antisymmetrized indices, these three antisymmetrized indices mu nu rho can be either three spatial indices I, j, k. They can also be 0, I, j, so one time-like and two space-like indices, but nothing else. They cannot be two time-like indices because you could get 0. So we have to consider these two cases separately. Okay. So in the first case, we have the identity 3 times partial I, f, I, j. Clearly, f, I, j, k equal to 0. Because this is fully antisymmetric, this would be the same if I multiply it by epsilon I, j, k. Okay. Just because of the same reasons that if when I contract something with two indices, antisymmetric and two indices, this projects over the antisymmetric part. The same happens if I project with a fully antisymmetric tensor, so antisymmetric in the interchange of any person, any other tensor. This means that I could remove these antisymmetrizers because they are automatic the moment this is contracted with epsilon I, j, k. Let me remove also this factor of 3 because it doesn't play any role. And now notice that this is constant, so I can put it inside of the partial derivative, and this becomes epsilon I, j, k f j, k equal to 0, but this is up to a sign and a number, what we have defined as bi. Okay, so this gives this equation in terms of the magnetic field, which is also what sometimes you write like this: the divergence of the magnetic field equal to 0, which is one of the Maxwell equations. The other, for the other choice of indices, okay, we have to we have 3. We expand this antisymmetrizer, and this is the derivative with respect to 0 of fij plus partial I f j 0 plus partial j f 0 I. However, we can write this as follows. I interchange these two indices, I get a minus sign, but I know that f0i is ei. Okay, and I also know that fjk is minus epsilon ijk bk. So I write this, then I have here and here I have the same thing, but with two different signs. So I get minus partial I e j plus the reverse. So let me divide it like this. I. Okay, this is equal to 0. Now we would like to get rid of this epsilon ijk. The best way to do it is just to multiply the whole thing by fijk, or if you want kij. So if I multiply this equation by kij, well, k has already been used, so I use lij or ijl, better because I have this in this order. Then I am contracting two indices with two indices. This gives me minus 2 delta kl, so minus 2 delta partial 0 of bl minus, and okay, this is antisymmetric in ij. We are multiplying by this, which is also antisymmetric in ij, so I get a factor of 2, and then this is epsilon l I j partial I e j, and this factor of 2, as I said. Okay, and this equal to 0. If I remove now the factor, so the global factor of minus 2, and I convert this into vector notation, then this would be the derivative with respect to time of b times a factor of c, of course, plus, okay, because we have removed the factor of minus 2, and this is the vector product of this operator times e. Okay, and what we have written above is the L component of this equation, which is the second promised Maxwell equation. Okay, what you have to remember, that as we mentioned before, is that you have two possibilities or 2 points of view. Okay, you can write f in terms of e and b, and then you need four Maxwell equations. Otherwise, you can write f as a function of a, okay, and then you only need two Maxwell equations, because the other two are equivalent to the Yank identity, which is contained in the expression. It's automatic the moment you express f as a function of a. Now we are missing these two Maxwell equations, but of course we haven't written any action, we haven't obtained any equations of motion from it, and this is what we are going to do next.